Welcome to eeNews video channel. I'm here with Stuart Yaniger and we are discussing OpAmps, operational amplifiers. Stuart, we all know amplifiers, but what is an operational amplifier?
Well, I'll answer that question two ways. An operational amplifier is generally defined by the way it operates, and I'll talk about that in a moment. A lot of people have gotten a bit lazy, and when they say op-amps, they mean specifically integrated circuit op-amps, little things like this.
Okay, yeah.
They're made even tinier today, and of course this is not good for somebody with eyes my age, but the canonical integrated circuit operational amplifier looked more like this, a little eight-legged gadget.
Yeah, and I remember that. I remember that one, yeah.
Yes, but again, an op-amp is defined by what it does.
But for now we have your drawing of an op-amp. Can you show it and explain what it is?
Yeah. Okay, an operational amplifier is defined by how it operates, what it does. It has basically three active terminals. There's power terminals too, but we usually neglect those for simplification. It has an output voltage and then two different input voltages. Now, the minus and plus on these inputs do not mean polarity in the sense that we think of as DC. They're actually polarity in the sense of which way does that output go depending on how those terminals are addressed. Okay. So, for example, if the voltage on the V plus terminal goes up, the voltage at the output goes up. If the voltage at the V minus terminal goes up, we get the opposite. The voltage at the output goes down. Okay, so this is usually referred to as an inverting input. This is referred to as a non-inverting input, and there is an output. That's the basis of op-amps. But an op-amp has one other interesting characteristic. Okay, and I'll get another one of my famous drawings. That this is what the output looks like. The output looks like some constant times the difference between those two input voltages. And what makes something an operational amplifier generally is that A is very large. I mean, very, very large.
Okay, yeah.
Okay, now, again, that's all it has to do. If it follows that equation, generally, if it has the two different inputs and an output, it's an op-amp, whether it's one of these, whether it's a discrete transistor module, like one of these, or even a vacuum tube module.
Okay.
It doesn't matter what the devices are, what the packaging is. An operational amplifier is defined specifically by having two inputs, one output, and the output is proportional to the difference between the two inputs.
Yes. Now,
if you've got that, you've got an op-amp.
Okay, but a normal amplifier also has two inputs, you know. Mainly one is earth and one is another connection. So one might say, okay, but you know, still not clear what the difference is between an operational amplifier and a normal amplifier, because how does this work? Is there a sort of off balance between those two then, or?
Well, many conventional amplifiers that you're talking about, normal amplifiers, are in fact operational amplifiers, or they have an operational amplifier within them. They're looking at the difference between that earth terminal, the brown terminal if you're an American, and the hot terminal. Okay, and all that matters is that difference. If they look at that difference, the output is somehow proportional to that difference. That's what makes it an amplifier.
Okay, yeah. Now you're mentioning the difference between these two inputs. Back in my long time ago, in my school days, I also learned about virtual earth, or in the US, virtual ground, I presume.
Yes. I know those Americans have a different word for everything.
Well, they're on different ground, of course.
Yes. Well, I should, while I'm thinking about it, also point out one other set of assumptions that we usually make about operational amplifiers, and then we can relate this back to what your question was about normal amplifiers. Ideally, an op-amp would have certain characteristics. Okay. Ideally, that A, which I said was very large, would be infinity. Okay? Ideally, there's no current flowing into these terminals, only coming out of the output. Okay? And because these have no current flowing in or out of them, the resistance, the input resistance, is essentially infinite.
Okay, yeah.
Okay, so that's usually a fairly good assumption, but of course, the art of electronic design is understanding why they aren't, and in which way they aren't, and how those are traded off.
Yeah,
If
yeah.
there was one ideal op-amp, that's all anybody would ever sell.
Yeah. But I think this virtual ground is important in understanding how to work with operational amplifiers and how to, you know, how to make circuits with them, because it's quite crucial to have a clear understanding what this virtual ground is.
Yes. Well, let's talk about that a little bit because it's a special case of an amplifier circuit. And I'll, in the next part, go into the amplifier circuits in a little more detail and see what fun things we can do with them. But a basic amplifier circuit made from an op-amp is called a non-inverting amplifier. And by non-inverting, here's your input.
Yeah.
There's a difference between the hot and the ground. And by non-inverting, it means that if the input goes up, the output goes up. The input goes down, output goes down.
Okay, so it follows each other. Yeah.
Right, it does not invert the signal. Now, if there are two impedances in this circuit, and I'm leaving these as generalized impedances, for simplicity, you can think of it right now as resistance, but we can do some fancy things with that. The fascinating thing, and this is derived in any electronics textbook, the fascinating thing is that you can write a very simple equation just using some basic Kirchhoff's and Ohm's law analysis here, and you find out miraculously that the output is equal to this very simple equation, which is a constant, times the input. You've made an amplifier with this term here as the gain. Now, what that means, too, is that because this gain is essentially infinite, there's really no difference in voltage between those terminals. That differential voltage is zero. So that if that input is grounded, there's your special case of a virtual ground.
Okay.
If the input is grounded, that's at 0 volts, the output should be at 0 volts. And again, tracing it through, you realize that this part right here, this node here, will also be at 0 volts.
Yeah.
Everything is forced down to that number because of that miraculous little equation that we get from the very, very large A constant in op-amp.
So if you're having resistors there, you know, you can do quite easily a sort of a small circuit, which actually, you know, says, okay, I want to have an amplifier 10 times or 100 times or 1,000 times. You know, you just pick out the right resistors and you put them there and it will give you that number.
Exactly so. You can just look at this equation and let's say that I want the output to be 10 times the input, then I just set 1 plus Z1 over Z2 to 10, or Z1 over Z2 equals 9. So if I make Z1 9 times bigger than Z2, I've got a gain of 10 amplifier. Very simple.
Okay, great. Now you're saying you can have impedance there, and for the simple conversation you say, okay, let's take resistors, but an impedance is much more complex. That can be anything. It can be a capacitor, or it can be inductance, it can be a circuit with, you know, a combination of these.
Well,
then frequency comes into play.
Yeah. No, literally the impedance can be complex, by which I mean an actual complex number. And as you've alluded to here, because I've left these as general Z's, Z can vary by frequency. It can vary in phase with frequency, it can vary in impedance with frequency. So let's say, for example, we have a capacitor here and a resistor here. Now, as we go up in frequency, that capacitance, the capacitive impedance drops on that. Okay, so it gets smaller and smaller, so the magnitude of that Z1 gets smaller and smaller. Z2 stays the same. So we can see that eventually our gain drops from whatever our initial value was down to 1. So we made something that changes its output with respect to the input as a function of frequency. That's your basic filter. And because Z1 and Z2 have a lot of flexibility, you can put in just about any kind of resistors, inductors, so forth that you want.
Yeah.
Then, in fact, you can make just about any kind of filter transfer function in the analog domain that you want to.
Thank you very much so far. Perhaps next time we're going into operational amplifiers and a ladder network. Okay, well, thanks very much for your introduction on operational amplifiers.
Okay, thank you very much, Vincent.
Okay, good to see you. Thank you. Bye-bye.